My throat isn't well, so I just try to be simple. Let's start. This is just for demonstration purpose. So the setup is not expected to be too difficult, and actually it's really difficult to operate on 4.0 beta because many habits will be changed since you can only shift A to search, and the search is not very good. I think the algorithm is being changed. Anyway, so let's create a maybe 5-5 plane, and I point distribute. Basically, the idea is just to take a noise to move them. Noise 3, and I only move them XYZ. So it should be vector mass to 110, and it's possible that we just evolute them. So I increase the scale. Yeah, something like that. It's a little bit awkward, but I think this is fine. And I point instance it. That's why I hate. Yes, this is fine. So I have this icon sphere, and I just increase the size subdivision and set shade space. And I'm giving every of them a different scale. So set the position, or I can set radius. Let's set radius. No, actually, this is a tricky problem. No, because the entire point of this setup is a dynamic radius solver. So I connect the geometry and I connect the scale, but I need to define the scale first. So let's take a random value, randomness. So average size is 1, and then if they move, I should time info. So they're moving. You can see it's a little bit fast. And then let's increase yet. You can see it's just bouncing up and down. But let's increase in the iteration because this is optimized. So actually it's fine that you just type in 1000. It's still very fast because the iteration will stop when the operation is completed. And it's a little bit too fast, but I think it's finishing its job. 25, 35. Yeah, you can see it's working. It might be better if I add a bouncing algorithm. Let's join geometry. So we visualize our plane. If I add a bouncing algorithm, then they will not get out of this plane. I think we can try, but the question is how complicated the algorithm it should be, and what's included within simulation zone. I think I'm only moving that within simulation zone, but I can keep this dynamic radius solver outside. So I put the simulation zone to include this set position, but I don't need the noise inside because I need to define the velocity when it bounces off. So what do we do here is that we take a store named attribute to store a velocity, and I can just use this noise 3D. I think I can get a seed for different particles, but I think it should be fine. It's just a random value, so I don't care. Okay, so I have this velocity, and I use this velocity named attribute velocity, and it's a vector to drive this animation. So now it becomes like this. You can see it's just going away as they should. Okay, and then I need to implement a kind of bouncy algorithm. Let's decrease the size. Okay, and then we need to implement a bouncy algorithm. I also need to decrease the scale of everything, because this is a simulation. Values are added every frame. So let's take a value position. So we divide this velocity by 10, so we can see this velocity. Okay, and when this velocity is hitting the wall, how do we define the wall? We use a recast. We have a cube. Let's make a cube. Let's just make it a 5, 5. And we probably want to define the radius before, so that we know that when it actually hits the boundary with its radius. So we store name the attribute. Actually, this is a good question. It is a good question. Because if the radius is changed, then the detection will fail. Isn't it? I still take a randomness. But that's a very interesting question, which is more complicated than I think. I take this radius. So I still need this dynamic radius inside. I can also set point radius. Another question is, I don't know which set point radius is working. I think this is a tricky question. I'm not sure, but let's just go with the store named attribute to control the radius. So I have this cube, and I start with myself. The redirection will be velocity, and the question is ray length. I think the ray length will just be this radius attribute. And if it hits, then we start to reflect the hit normal. So here we take a switch, and I need to switch with a vector. So this is it. So we can try, but I think it will fail. And I use this new radius So now it's going like this. This is kind of ugly, which I didn't think it will, but the question is why? Oh, because it bounces off, it should redefine the velocity. So we store a new named attribute, and we use this new velocity. We can use the same velocity actually. Then it becomes like this. And then we turn on this dynamic radius solver. You will see lots of problem. Firstly, this is working too fast. So I think I decreased the scale by another. It's not 100% perfect, but it's working. And sometimes you can see it's very glitch because the scaling is too exaggerated. So I think I turned down the scaling factor, maybe 15.5. It will take a little bit more time to calculate, but it will make the animation a little bit smoother. It's not 100% perfect. Yeah, you see, previously, just a few seconds ago, like it's not really hitting the wall, but it bounces off because the radius is actually being changed with this dynamic radius. Initially, it's looking like this, so it bounces off. We can fix this problem by storing new named attributes inside and do the dynamic radius solver inside. But I'm not sure if I need to progress that far. So here, let's give it a try. Basically, we need to change the radius before this raycast evaluation. So we put this dynamic radius solver before, and we use this radius to control the radius. And then we need to change the radius inside so that this radius is being changed. So we store named attribute and its radius. We plug the scale into. So now we have kind of a proper bouncing, that if they are scaled down, they will bounce with this relative radius or this new radius. But the issue is that they will not really recover. So we need them to bounce back. So we need to redefine the radius. But the question is, when do we redefine this radius? So we need to define that they have no collision when they expand again. So I take a, let's say, multiply. And I need to multiply kind of by a percentage over 1. So let's take a add. So 1 add a division by 100%. Basically, we're creating a margin. So we take a value. So this is about 5%. So we take a 105% margin, and to see if they collide. So there's a collision detection radius. This is basically what's doing the collision detection inside this dynamic radius solver, and also the relaxation solver as well. So relaxation is more kind of rigid body-like, but the dynamic surface sampling is, or dynamic radius is what you see now. So if we have this new radius and it does not collide, then we do a switch. I think I can do the selection. Let's try. So basically it says that if I expand and they do not collide, then I will rewrite this radius with this new expansion. So you can see that they scale down, but they will have a tendency to scale up if they do not have a collision. But you also see the problem that these balls will scale up unlimitedly. So we want to clamp this value with this original radius. So while we are changing this initial radius, we need to define what's the value of original radius too. And this original radius is not being changed. So here, let's take a radius, and I want to clamp this value must not exceed this original radius. So the maximum value must be its original radius. So you can see it's not expanding itself, but it will recover back and it will bounce accordingly. I think there's still some overshoot problem due to certain kind of reason, which I'm not too sure. Is that due to perspective? No. I'm not 100% sure why it's still overshooting. Oh, it's probably because the velocity, the detection is from this ray at the direction of yet. So I think it might be easy just to add a border, a margin to the detection. Currently, this entire issue occurs because we are recasting in the direction of velocity, but the point of collision is not necessarily in this direction. It may be on the side of this direction. So recast is not really a good method here. Here we need to search a position of contact in the radius. So what we do is use geometry proximity, and I evaluate on face. So I have the position of the contact. So instead of using the reflect, if it hits like this location, it should go the opposite direction. So I take the position. Do I have a position? No. So I take a position to subtract this position of contact to generate a vector, and I need to change the detection. If this distance between my point and the collision point is less than the radius, less than or equal to the radius, then I will use this new subtraction result. Okay, so now if I play, you can see they're going very fast because the magnitude is not taken into account. So we normalize it. So firstly, we make all vectors, all lengths into one, but we redefine this length using the velocity. Where is my velocity? Yes, I use the length of the velocity. So even if they bounce off, the velocity or the magnitude of this vector will be the same. So now we should not really see any part which is going out. So I think it's fine now. And yeah, it's working fine. But we start with a point which is getting out. So I think in this case, we can do another geometry proximity, and we delete this point. So this is the same if the radius, so if the distance is less than the radius, we delete this point. So the point is being deleted. Okay. I think this is fine now. There's one last problem, however, that if the velocity is very fast, so maybe let's make that to divide it by 10. You can see if it's very fast, it will go outside, because we only do evaluation once and we do not have subframe in simulation zone. So the best method is just to decrease the velocity for the moment, and in case it happens, then we can use this recast. If my point is not hitting, hitting the wall in the direction of velocity, it means they are going outside this box, then we can delete this point. If it does not hit, then it will delete, and I can remove this redirection. So this is the effect, that if they go outside, they will not hit the box in the direction, so they will be deleted. So now you only have this kind of stuff. But it will always be better if you start with slow velocity, since we do not have subframes in geometry nodes yet. So I think this is yet. Essentially, the entire point of this animation is just to demonstrate the point of this dynamic radius solver. So I hope you enjoyed this video. I'll probably see you next time. Bye bye.